Hi guys. Everybody into the meeting here.
Hello.
How you doing?
Doing well.
Let's give it a minute for other people to join, then we'll start.
All right.
Let's see. I don't know if you guys saw my announcement last night, but I'm going to go over the exam in office hours today. So I want to, invite everybody if they have questions about how things work, what was the question that was being asked, if you had trouble with, certain questions on the exam, please come to the office hours. I'll also record it so I can post it up on our Blackboard page. So in case you can't make it, but you want to see it later, I highly recommend that. That'd be helpful. The stuff on this exam is really indicative of the things that you will see on the final exam. Okay, so make sure if you had trouble with some of the questions on it, come to the review or at least take a look at the video later so that you can get a heads up on how these things are supposed to work. Okay, basically, quite a number of you did really well on the exam. The median for the exam was like 85 or 86, I think, which is really good. There were some people who had trouble on some aspects of it, mostly the joint distributions. And so if you want to come to the review, that'd be really helpful, I think, for you to be able to make sure that you get that. So you don't, the final exam is worth quite a bit of our grade. Final exam is worth like 30% of our final grade. And each midterm exam, I think, is only worth about like maybe somewhere between 10 and 20%. Maybe it's like 15% of our overall grade. So it's not as much as the final exam, but like I said, a lot of this stuff will be on the final. So make sure that you have it. Let's see, I think that's about it in terms of administrative stuff. I haven't graded the homeworks yet. I'm sorry about that. I got caught up in other stuff. I'll have those grades up today so that you guys can take a look at that. Plus, I'll look at old homeworks as well. Take a look. We have a new homework assignment for this week. Okay, that's going to be due at midnight on Thursday. Again, we'll have another quiz on Thursday. I know the summer classes go really fast, and it's hard to keep track of things. And this class is set up so that we have a lot of assessments. That's just to make sure that people don't fall behind on things, and then also so that you kind of get a feeling for how could you be tested on this material. Okay, kind of gets you prepared for the final exam, and also kind of helps you bring all the material together in your mind. So keep that in mind. We have a quiz on Thursday. Homework is due Thursday night, and we're just going to keep moving on the material. Okay, so today I'm going to continue on talking about chapter 5.3. We've got about the rest of the chapter to cover. There's quite a bit of stuff, and then we'll start in on chapter 5.4. 5.4 is really short, so we'll probably be able to do that today, and then tomorrow we'll start chapter 6. I just want to throw out to you guys to keep in mind, I can't believe it, but it's June 1st, and we basically have 3 more weeks of lectures. Now remember, we've got 4 lectures in each week, so it's still quite a number. We're about halfway through the semester right at this point, but we have 3 more weeks of lectures, and then we go into the week of final exams. I've been working with the course coordinator and the other instructors for the class to talk about the final exam and how we're going to schedule it. We're still trying to decide when that's going to get scheduled, because the registrar, now that things are online, I don't think the registrar has actually scheduled an exam for this, so we're going to be trying to figure that out, and then I'll let you guys know as soon as I know, okay, about the final exam, when that's going to be and how that's going to work. Okay, so with that said, let's go back to talking about chapter 5.3. So I've got my lecture examples for 5.3 here. I just want to quick summarize some of the stuff that we talked about last week with 5.3. This here, let's see if that's with 5.3, and then we'll move on to other stuff in 5.3. So 5.3 is about basically coming up with confidence intervals for our parameters. Mostly we tend to look at confidence intervals for our mean. Okay, so we're given some kind of information, like on example 1. Let's just summarize. So on example 1, we have a population group, and it has a mean and a standard deviation. We want to compare that population group with another population group that has its own mean and standard deviation. And we want to look at like a 95% confidence interval around this mean here. And so what we're doing is we're saying, right, So 29.2 is the mean for our sample group, okay? 95% confidence interval around that 29.2 basically says, right, if this is normally distributed, which we're assuming all of our data is normally distributed, okay, then I've got this normal distribution, 29.2 sits right in the middle on that. I've got 95% of the area under that curve centers around that mean, 29.2. So to create that confidence interval, I'm looking at values. You know, if I were to translate, I have a z-value here and a z-value here. If I were to translate that into actual mean values, okay, I'm going to go 29.2 plus or minus my z-value associated with the 95% confidence interval. How we get the z-value is, I have this area is 0.95, the remaining part of the curve, okay, I go 1 minus 0.95 gives me 0.05. That 0.05 is split between this tail and this tail, the upper tail and the lower tail, okay. There's symmetry in our normal distribution, so it's split equally between these two, okay. So I look on my z table, okay, here for 0.025, and I find it 0.02, where am I, right here, 0.025, and I find the corresponding z value that associates with 0.025, okay, that's plus or minus 1.96, okay. So on the low end, I have minus 1.96, on the higher end, I have positive 1.96. That gives me my z value. I need to translate the probability into a z value because my z equation, this whole thing for my confidence interval comes from my z equation, okay, of my z equals, right, all the whole z equals discussion that we had when we derived this. Okay, this was from our notes last week, okay, came from this derivation right here, okay, for our z equation. Now, I translate that, okay, from a probability into a z-value. That z-value helps me calculate a 90, in this case, 95% confidence around 29.2 plus or minus. Okay, we've got our standard deviation, we've got our sample size. Okay, that basically says, right, 29.2 sits in between these values right here. Okay, one of the things that happens is we're going to start using confidence intervals to talk about statistics. Is I have this 27.89 to 30.51. Okay, that's a 95% confidence interval around 29.2. I look at that and I say that other population of people who are not road workers, right? That's they have a mean of 18.2. 18.2 is not contained within this confidence interval, right? So that means I've got a 29.2 confidence interval, and I'm going to have another confidence interval around my 18.2. And because 18.2 as a mean is not within this confidence interval, I can say with 95% confidence that this mean is significantly different than that mean, 29.2 and 18.2, okay? But we needed to do a confidence interval around that in order to make that assertion, okay? So we're starting to get into the statistics portion of things, okay? So this is one way of thinking about it, which is our confidence interval, okay? So it's just a really quick review of the stuff that we talked about last week. And we're going to use this stuff. We're going to do some more examples for confidence intervals. Okay. All right. So turning the page to my next one, which is example 2. Okay, so we've got these right there. Good. All right, so example 2 says, put that in focus as much as we can. I did do that's weird. There. Okay, so example 2 says we've got these points, 6.5, 9.2, 9.9, 12.4, and these points are all part of a normal distribution, right? So our probability density function, okay, comes from here, okay? And then we're given essentially a sigma, right? So our sigma is equal to 0.8. Okay, we can see that here within our equation, okay? So this is 1/2 radical 2 pi times our sigma. Times e raised to the minus 1/2 y. This is like a y sub I minus u, a mu, divided by 0.8 quantity squared. Okay, we've got values for y. So this is our probability density function for our normal distribution. Okay, this is our normal distribution curve. Okay, so we've got a sample size of 4, and these y sub i's right here. Actually, I called them y, but this I can actually call this y here. These y sub i's, okay, are from a normal distribution, and the mean is unknown. It's a little bit, it's kind of academic to say, I I know what the standard deviation is, but I don't know what the mean is. We're going to talk as we go along. What do we do when we have unknown means? When we have known means, how do we calculate these things out? But for now, we're just trying out different ways of solving these problems. Okay, so I've got a known standard deviation. I've got an unknown mean. What values of our mean are believable given these 4 data points? Okay, so let's talk about how we're going to solve that. Okay. All right, so let's start taking notes. So I need to come up with some kind of an estimator for my mean value. So I'm going to think about, we have to calculate a maximum likelihood estimate for our mean value. Okay, so we talked about maximum likelihood estimates. We talked about them in terms of normal distribution. Okay, there was a certain, we already kind of proved how we can calculate our mean for our normal distribution. So for our MLE for that is going to be, we'll call it mu sub e, which is the same thing as mu hat. Okay, which is, we'll call it, it's just the average of our samples. Okay, so this is going to be 1 over n. I equals 1. In this case, it's to 4. And I've got y sub I. So I'm going to sum up all of those y sub i's, and I'm just going to take their general average, which is 1/4. I sum them all up to 38. Divide that by 4. I get 9.5 is my mean, my estimate for my mean. Okay, maximum likelihood estimate. So now we need to calculate a 95% confidence interval for our mean. And why did I choose 95%? I wasn't told what confidence interval level to choose from. 95% is your most common one. It's also the most middle ground. Typically, we're gonna, as we move into statistics, you'll start to see like what alpha levels we start to choose from. The alpha level that goes with 95% is 0.05. That's usually our minimum alpha level that will detail something is significantly different from something else. When we do 90% confidence, it's a little bit too loose. 99 can be too strict. Okay, so 95 is kind of like a happy middle ground for that. So that's typically why, if you're not told what level of confidence to use for things, 95% is typically a good first step to choose from. Okay, so we have a 95% confidence interval for our mean value, which is what we're going to start to calculate here. There we go. So let's go ahead and head into that. So I need to think about, I've got a 95% confidence, which means my alpha is 0.05, because remember, it's alpha is equal to, so 1 minus alpha times 100% gives us our confidence interval percentage. Okay, so alpha is 0.05. Now remember our curves, so 95 is going to go here, so that means I split up 0.025, 0.025. Oops. So I split that up, so I need to be able to look at my z value that corresponds to alpha over 2. So this is going to be a z value that goes to 0.025, right, because I cut the 0.05 in half. So I look up here, remember, right, we're looking for 0.025, which we said was right here, 0.025, and I want to be able to look and see what z value that's going to correspond to. Okay, so that gives me a z value of basically, we're going to do both, it's positive and negative, 1.96. Positive and negative because I've got my lower bound and my upper bound on my confidence interval that I need to take into account. Okay, but there's symmetry. So once you find 0.025, take that value and then you're going to make the positive and negative portion of it. Okay, so now I'm going to take a look at the probability that my y bar minus 1.96, that comes from our z value. I'm going to start plugging things in. 0.8 divided by radical 4. Okay, so this is my standard deviation divided by square root of n. Okay, and this is going to be, mu is going to be less than that. Mu is going to be, mu is going to be greater than our lower bound, and it's going to be less than our upper bound. Y bar plus.
I have a question.
What's up?
So if we're saying that we're mostly going to be calculating a confidence interval of 95%, is our z value almost always going to be 1.96 then?
Exactly. So for 95% confidence interval, the z value that corresponds to that is 1.96. we'll talk about what the z-values are for two other common ones, like 90% confidence interval and 99% confidence intervals are also common. We'll just write down what those z-values are, but yes, when you're dealing with a 95% confidence interval, your z-value is plus or minus 1.96, and that comes from our z-table, right? So remember, the 95% has an alpha of 0.05. That alpha 0.05 gets split. See, the alpha 0.05 gets split into 0.025, 0.025 because of the symmetry on our curve. So I go to my z-table and I look for 0.025, right? So that corresponds to 1.96 for a z-value. Okay, so that's where that's coming from. It's not coming from thin air. It's actually the z-value that corresponds to 0.025 on either end. Okay, so now I need to calculate these values out in order to find my 95% confidence interval for that. So write that down. So my y bar is my maximum likelihood estimate. We said was 9.5. Okay, so then my given this y bar from our sample size, our interval. Sorry, I can spell interval. Is going to look like this. I'm going to go 9.5 minus 1.96, 0.8 all over radical 4, comma 9.5 plus 1.96, 0.8 over radical 4. Okay, so that's the interval that my mean is going to be within, based on my maximum likelihood estimate. We're going to talk about that in chapter 5.4, which is if we have these samples, right? I'm working with the samples, 6.5, 9.2, whatever. Now, how do I know that those samples give me a good estimate of what's actually happening? We're going to talk about that in 5.4. All right, so now adding these things up, I get 8.72 to 10.28 right here. So this is a 95% confidence interval for our mean. So what this means, I'm going to translate this into like English, right? So what this means is I've got this sample, 6.5, 9.2, 9.9, 12.4, I've got this set of samples. Find out a maximum likelihood estimate of my mean based on these samples. It's going to be just the general sample mean, so 9.5. I summed all those up, divided by 4, I got 9.5. Given that my sample mean was 9.5, I'm 95% confident that my true mean, which is mu, is within the bounds of my sample mean. Okay, so I'm 95% confident that my true mean is between 8.72 and 10.8. Given that my samples had a mean of 9.5, and given that I'm using a 95% confidence interval, that's how we think about what this method is telling us. Okay.
I have another question, sorry.
Okay.
It's regarding the interval notation. So how come this time we're using the not including 8.72 and 10.28 while in example 1 we did include the endpoints?
I see. Oh yeah. So yeah, that's and they do include both. I see what you mean. Like, how come we're using these brackets instead of these here? Technically, in statistics, those are going to be the same thing. Remember when we deal,
okay.
yeah, because remember when we deal with especially with continuous data sets, right? We're dealing with an integral. Okay, so when I integrate from A to B, I'm including my endpoints along that. So yeah, I was these things in statistics when we're talking about our intervals. All we're saying, we're definitely including these things within that 95% confidence interval. So that's a great question. And you can consider them as being inclusive for how we're thinking about the data here.
Okay, so in statistics, any interval notation means inclusive.
Right, because what we're saying is it's still all like it's not definite, right? I'm only 95% confident that my true mean is within the bounds here, 8.72 to 10.8. So maybe the true mean is at 8.72, right? Or maybe the true mean is at 8.73, or the true mean is at 10.1. I mean, it's like you get the idea, right? What we're saying is we don't know really where our true mean is. Okay, we're talking about based on the sample size. I'm 95% confident that my true mean is within the bounds here, surrounding my sample mean, essentially. When we start to get into statistics, it's kind of like we don't really have definites anymore. We can't say for sure this is the value, this is the weight, or this is the mass, or this is the velocity, or this is the something, based on all the, you know, the trajectories and what I'm actually measuring. When we get into statistics, we're talking about more kind of nebulous, right? I'm 95% confident this is true. I'm 99% confident these things are significantly different. I'm whatever, you get the idea, right? So all we can do is state our assumptions, right? And my assumption is that this data is normally distributed, which allows me to use this distribution, okay? And it allows me to use this as a maximum likelihood estimator, okay, for what I'm looking at. And then I can, because I'm making these assumptions, I don't actually have a definite value, because ultimately what's happening is, if you think about it, just take a step back in real life, right? It's not feasible for me to go out and sample the whole population, 7.5 billion people. I can't sample the whole population. I can only sample some subset of that and then make general assumptions about what the whole population is doing. Okay, so that's why we start to get into the bounds of, well, I'm 95% confident this is true, right? There's no absolute anymore. Okay, so kind of get into the realm of stating what your assumptions are, okay, and then being able to state, you know, based on your assumptions, how confident are you, okay, in what you're proclaiming to be true. Okay, does that make sense?
Yeah.
Okay, great. So let's take a step back and think about things a little bit too, and then we're going to talk about, so we talked about our values for our continuous data sets, right? We talked about our normal distribution, but let's talk about proportions, right? So if we have some kind of a binomial, you know, experiment that's happening, where I go out and I sample a bunch of people and I say, here's a question, yes or no. So let's talk about how we set up our confidence intervals for that. So our confidence intervals for a binomial parameter. We're going to call our binomial parameter P. Okay, that P stands for our proportion. Okay, so let's talk about what things are. Right, so P is our proportion of what we call success, which is yes answers in our binomial experiment to the total number of trials, right? And that's going to be our n value. Okay, so yes answers will be our x in terms of our random variables, and then n will be the total number, right? So say I go out and I poll, you know, 350 people, 200 of them answer yes to whatever question I'm asking. My proportion is going to be 200 divided by 350. That's going to be my proportion. Okay, so that's how we're thinking about our P. So again, we need to think about our maximum likelihood estimator for P. So we think P hat is our maximum likelihood estimate for P. Now, why do we do P hat? It's because this is again where I'm taking a sample to represent a whole population, right? So P represents going out and polling the whole population of people saying yes or no, okay? I can't reasonably do that. It's just not feasible for me to go out and poll everyone. So I'm going to sample some subset of that, right? I'm going to get this based on my results of my experiment. I'm going to get my maximum likelihood estimate for my population proportion. So that's where the P hat comes from. And remember, P hat is equal to simply x over n. Okay, so this is in my experiment, right, the number of people who answered yes over the total number of people that I've polled. Okay, so my P hat is just simply x over n. Okay, so now let's think about our confidence intervals for this. Okay, so as we do for large random samples, we want large sizes, right? Because I want to be able to have my binomial shape into a normal distribution, right? So if the law of large numbers says, right, as I gather more and more and more data, then my binomial experiment kind of shakes down into its natural, normal state. So for large random samples, the 1 minus alpha times 100%, this is our 95%, 99%, whatever confidence interval. for a population proportion P. Right, so remember, we're dealing with samples to relate to a population again, just like we did with our normal data. Okay, so this is going to be my p hat, my estimate, minus z alpha over 2, p hat, 1 minus p hat, all over n. That's all in a square root. Okay, it's going to be less than or equal to p, which is less than or equal to p hat, plus z alpha over 2, p hat, 1 minus p hat, all over n, all inside the radical. Okay, so this now is going to give us, and in a big box, our 1 minus alpha times 100%. Okay, that comes from our z alpha over 2 confidence interval for our population proportion. P hat is our estimate, okay, for our population proportion. Okay, so we're going to go through. I'm going to talk about like where this comes from, just like we did with the normal distribution. We're going to this is your equation that you want to think about. I'm going to put a big, you know, a bunch of stars around it. That's the thing that you want to circle because that's the thing that you're going to want. I'm going to start posting a formula sheet for you guys, so you guys can start to see when I teach this class and it's not online. The formula sheet is something that students are allowed to bring into an exam, and then they can add things to it. So this is something, this is probably going to be on your formula sheet already, but you can make note of like what it is. The formula sheet can help you kind of like aggregate all the different formulas that we're accumulating as we go along in this semester. Okay, so this is something that you definitely want to keep in mind. But let me just talk about like where it comes from, just like we did with the normal distribution. Okay, so let's talk about that. So we're gonna we've got a sampling distribution of our mean values, and our central limit theorem basically allows us, as our n gets really large, these things shake into a normal distribution. So I can start to say my z value is equal to my x bar minus my mean, all over sigma divided by radical n. This is our normal distribution, which we say is n01. Okay, remember our standard normal has a mean of 0 and a standard deviation of 1. Okay, so we normalize our data so that I can get it into this form. So I can just use a lookup table. Just that single z lookup table will give me my z and my probability values, but it allows me basically to compare, you know, all sorts of different types of mean values, you know, using just this one normal table. Okay, so let's think about this in terms of our proportions. Give myself room here. All right, so what this means is our z. So for proportions, this is going to look like our p hat minus our population, right? Our population proportion is equivalent to our mean. Our p hat, right, is our maximum likelihood estimator, which is like our x bar. This is p times 1 minus p all over n, all that's square rooted, okay? Right, so let's talk about where each of these things are, and this is our z value for proportions. I'm going to put a box around that because you're going to need that, okay, when you're calculating your z value for proportions. So how this is correspond, this is like our x bar is like our p hat, our mu is our expected value, right, which is our p, and our sigma squared, our variance, is equal to p times 1 minus p. How come I only have, you know, a single n instead of npq, all this kind of stuff? It happens when you derive all this out, with x over n, all these things. Basically, I'm not showing you how I got to here, okay? But it comes from all the n's that are inherent within here, and then basically things that cancel and don't cancel. And we're left with, at the end, square root p times 1 minus p all over n, okay? And that gets divided into p hat minus p. That's our z value, okay? And this is for large n values, okay? So what we want to do is we're going to use this, we're going to plug this into our probability of z alpha over 2. Does everybody have this? I'm going to turn the page here. Anybody need more time?
Yeah, just to copy the right hand.
I'll give you a sec.
Okay, I'm good.
Okay, anybody else? Okay. All right, so we're going to put this into our probability Z alpha over 2. So it's going to look like probability minus Z alpha over 2 less than or equal to P hat minus P times 1 minus. This is like what we did before, okay, for our continuous values, which is alpha over 2. And that's going to be approximately equal to 1 minus alpha. Okay, so it's our 95%, 99%, 90% confidence interval here. Okay, so I'm going to just take this stuff out of my probability and I'm going to work with that bit right there. Okay, so how that's going to look, okay, this is going to be minus Z alpha over 2. Just so I can do the math more easily, I'm going to take it out of the context here and then we'll put it back in the end. So essentially what I want to do is I'm going to multiply both sides by this denominator here. Okay, so what I'm going to get is minus Z alpha over 2 times 1 minus P. Okay. So all I did was multiply both, right? And now what I'm going to do is I'm going to subtract, right, my P hat from both sides because I'm ultimately solving for P, right? I want to find the 95% confidence interval around my population proportion. That's my goal. So if I subtract P hat from both sides and then I divide by minus P, okay, so let's do this. I'm going to get minus P hat. Goes 2. Okay, and now I need to divide by minus 1 on both sides in order to solve for this. And I'm going to flip my inequalities as well. So it ends up looking like P hat minus Z alpha over 2. You don't have to do this derivation when you're doing the work. I just wanted to show you where it all comes from. Okay, good. All right, so now we've got our P, our population P is between P hat minus and P hat plus, okay? But the thing is, I want to call your attention to this part right here. These P values are with our population proportion. And we don't know what the population proportion is, right? That's the whole goal, is trying to figure things out. So what we're going to do is we're going to substitute with our P hat, okay, in here. So I've got P hat plus or minus Z times P hat, 1 minus P, and that's going to give me a confidence interval around my population proportion. So then I'm going to put them back into my thing. So I'm going to get P hat minus, Z alpha over 2. So P hat 1 minus P hat, because that's ultimately what I know and what I have, my sample, less than or equal to P, which is less than or equal to P hat plus Z alpha over 2. Okay, and this is what's going to give me my confidence interval around my population proportion. My population proportion is greater than P hat minus, and it's less than P hat plus. Okay? And I can say that with 95% confidence, or 99% confidence, or 90% confidence, whatever confidence interval we choose. Okay, so that's how we're thinking about our population proportion. It's the same derivation that we used, okay, when we were talking about our normal distribution or continuous data set. Okay, so this is dealing with a binomial or discrete data set. Okay, but remember our law of large numbers says Okay, as my sample numbers get bigger, okay, right, my discrete values approach a normal distribution shape. Okay, so this is where we're coming from. That's where our confidence interval was coming from. Okay, so when you guys are done writing that down, we're gonna take a look at example 3 on our lecture example sheet. Anybody need more time to write this down? Okay, good. All right. So my example 3. So example 3 says we've got a poll of Pennsylvania residents, and it showed that we surveyed 418 people, right? Out of that 418, 280 supported a given ballot measure, whatever it was. We're going to use the sample proportion, 280 out of 418, to estimate with 95% confidence our parameter P, our population of all Pennsylvania residents who are going to support this ballot measure. This is a really common thing, right? You know, political groups don't have time, they don't have the ability, they can't even get in contact with all of the people, say within a given town or within a given area or within a given state. So what they're going to do is they're going to sample some subset of that, and then they're going to make you know, extrapolations, right? Statistics based on that sample size. So that's exactly what we're going to do here. And we're stating we're going to use 95% confidence. Okay, we're going to call X as our random variable. We're going to say this is the resident, these are the number of residents who support this measure, our ballot measure. Okay, so this X value is equal to 280. Okay. And our total number of people that we polled is 418. Okay, so that means that my population, my sample maximum likelihood estimate, okay, is going to be my 280 out of 418, right? These are the people who said yes. Yes was given the equivalent of a success, which is equal to a 1. If they said no, that was given a 0. So when I sum up all of these ones and zeros, I'm summing up to 280. So 280 over 418, which is basically equal to 0.67. We're going to deal with the decimal, okay, 0.67. So now we're going to do a 95% confidence interval, CI for confidence interval. And what that means is our alpha value is 1 minus 0.95, which is equal to 0.05. Okay. Now remember, this is right? So this is 0.95, okay? I have to split this alpha into 2 pieces, into 0.025, into 0.025. So I'm looking for an alpha over 2, which is 0.025, whoops, 0.025. So I need to find the Z value that corresponds to the alpha over 2, okay? So my Z alpha over 2, remember we look on our chart for 0.025. And we find the corresponding Z value that goes with that, and that's equal to basically that's equal to plus or minus 1.96, right? Minus for the lower end, positive for the upper end on our normal graph here. Okay, so our P hat, right? P hat minus Z alpha over 2, P times P hat 1 minus P hat all over N, okay? And our population is going to be between this plus or minus P, parentheses 1 minus P hat all over N. Okay, so I'm using that formula to say, you know, with 95% confidence, where's my population proportion going to be? Okay, so let's plug in the values that we have, all these different values. Let's plug them all in and see what we get. So this is going to be 0.67 minus 1.96, right? This is going to be 0.67, 1 minus 0.67 all over 418 square rooted, or equal to P, which is less than or equal to, same thing, 0.67 plus 1.96. I'm running out of space. 1 minus 0.67, sorry about that, 418. Okay, I ran out of space a little bit there. So I'm going to add everything up, okay? And it basically finds that my p-value is between 0.625 and 0.715. Okay, so that means, let's write this as an interval, 0.625, 0.715. Okay, so that means that our population proportion, I can say with 95% confidence that my population proportion is between 0.625 and 0.715. Let's write that in words so we kind of get an idea, like, what does this actually mean? So that means that we can be 95% confident that 62.5%, 71.5% of the all, let's say all of Pennsylvania residents support the ballot measure. Right? We've taken a sample of people, 418 people, and we've come up with a 95% confidence interval with how all of Pennsylvania residents are going to respond to this particular ballot measure. Okay, I can be 95% confident that between 62.5 and 71.5% of the population is going to support it. That's not bad, right? That's more than half, which means it stands likely that it'll pass, right? Based on the data set that we're working with here. Okay. Anybody have questions on what we did? We did one continuous, we did one discrete. Okay, one with a discrete is our population proportion. Okay, and continuous is we've got some kind of continuous data set that uses our normal distribution, right, as a probability density function. Any questions? Anybody need time to keep writing before I move on to our notes again? No? Okay. I will print these, scan these in and put them on our webpage. All right. So a related topic to confidence intervals is a thing called margin of error. We hear that talked about when we're dealing with, especially with political polling, right? We've got some kind of margin of error around our data set. Okay, so let's think about what that is. We're going to write down. So this is essentially our maximum error of the estimate. Okay, it's I will write down some definitions of it and then we'll graph it out so you guys can visualize what it means. So it's like our maximum likely difference between the point estimate of a parameter and the actual value of the parameter. Basically, it's related to a confidence interval, right? So we don't actually know what our actual values are for our parameters. Okay, we can only come up with estimates and confidence levels and margins of error around what these things are. So it's related to confidence intervals. Okay, it's basically, I'll write this down and we'll draw a picture. It's half the maximum width of a confidence interval. Let me draw a picture so that you can see what I'm talking about. Right, so we've got our normal distribution, okay? And then we've got like our mean value that's happening here, okay? And then I've got values here and here, okay? So let me get another. So this, let's say, is our confidence interval, right? So this whole thing here right? This is, remember, this is our minus z value. This is our positive z value, z alpha over 2, positive z alpha over 2. Okay, so that gives us like our 95% confidence interval or whatever. Okay, so now our margin of error, okay, this is margin of error. Okay, and then this is our margin of error. Okay, so our confidence interval is this whole width right here. Okay, my confidence interval is that whole width. My margin of error is half, so it's from my lower bound to my midpoint, to my mean, and from my mean to my upper bound. Okay, so that gives me my margin of error. So we say plus or minus margin of error, right? Basically, if my margin of error is half, right, I can double that and give me a confidence interval length. Okay, so let's pull this up. So just I'm going to put down some values. You're asking me about like standard values for confidence intervals. So let me just write down. So 95% confidence. Sorry, 90%. 90% confidence means my alpha is equal to 0.1, which makes my alpha over 2.05. I look up 0.05 on my table, and I find a z alpha over 2 value of 1.65. Okay, you can get these all from the table. I'm just going to summarize because we're going to use these a lot. I don't want to have to be looking up in the table the whole time. So 95% confidence, we've done this already. Our z alpha over 2 is going to give us 1.96, right? Remember, we do for a confidence interval plus or minus our z value. 99% confidence, right? So my alpha is equal to 0.01. I cut that in half, right? I look it up. I get a z alpha over 2 equal to 2.58. Okay, so you can get a feeling for what these z values are going to look like. Okay, all right, so let's write out our width of our confidence interval, and then we're basically kind of deriving, right, where our margin of error is coming from, just so you can kind of see. We'll do it both for data and for proportions. Okay,
Could
so
you have a 100% confidence?
well, so that's a great question. It's kind of like technically speaking, our normal curve, right? This normal curve right here, right? It's the area under that curve is equal to 1. We sum it all up, the area is equal to 1, right? That's our 100%. But this thing is asymptotic, right? And it goes on forever, right? But it's asymptotic to my x-axis, right? So it approaches 0, but technically it never gets there. I'm exaggerating because as it gets closer and closer to the x-axis, you don't see the difference between them. So to say that I have a 100% confidence is basically like saying I know exactly what my mean is. I've polled the whole population and I know what it is. It's not really feasible to calculate out. If you guys saw that on the test, that where we had like z values that kind of went off the table, okay, that basically gave us 100% confident, 100% probability something was going to happen, or 0% probability something was going to happen. Okay, it's so far off the charts, right, as to be virtually guaranteed or virtually guaranteed to happen or not to happen, depending on which end we're talking about. So it's not really feasible to say I have 100% confidence that this is what it is, unless you can say I've pulled everyone in the United States because that's my size, or I pulled everyone in the globe and now I know exactly what my population value is. So you don't really say that. The closest we usually come to is 99% confidence. Because even with a z of 0.25, we're talking about my endpoints being like way out here on my graph. So you're essentially getting the whole thing, okay? But remember, our normal curve goes to infinity in both directions, right? And that summing up from minus infinity to positive infinity is going to give us that 100%. And it's just not really realistic. Does that make sense?
Yeah, thank you.
Yeah, so mathematically we can do it, but realistically in the real world it doesn't have much meaning. So that's why we talk about the highest we can really get in terms of confidence is 99%. And that's a really tight value. Okay, so let's talk about our margin of error. So our width, okay, so our width of our confidence interval, this is how we're kind of deriving our margin of error. So our width comes from, right, I need to look at my upper bound minus my lower bound, right? So to get this, I find out what this value is and I subtract that value, and that's going to give me the width of our confidence interval, okay? So I'm going to say I've got x bar plus the alpha over 2, sigma over radical n, right, minus, this is our upper bound, minus our lower bound. Right, to give us the width of our confidence interval. Upper minus lower is going to give us that width, okay? Now, basically what that means is our width, because we've got symmetry here, right? So with symmetry, I can say this is equal to 2 times z alpha over 2, sigma over radical n, right? And then my margin of error, right, is essentially my width divided by 2, right? So that's width divided by 2, which is equal to z alpha over 2, sigma over radical n, right? I got that because I divided both sides by 2, and I get width divided by 2, I get z alpha over 2 times sigma divided by radical n, and that gives me my margin of error. Okay. All right, so that's for like our continuous data set. I'm going to talk about it in terms of proportions. Okay. Are you guys okay with this part right here? That I'll put a box around it. Like this, maybe so you can see it if you're still writing. Okay. All right, so now for proportions. Okay, so this gives me my maximum width, this part right here, this equation. Okay, so proportions, right, I've got my x bar, instead of x bar, it's equal to, we're going to call it k over n, where k is like the number of successes, right, the people who said yes, they answered yes, n is our total number of sample sizes, right. My sigma is equal to k over n times 1 minus k over n, right, this is our p hat, this is 1 minus p hat. Okay, this is where things are coming from. So using k values, I'm going to plug them back into my width. So my width is equal to, still again, upper bound minus lower bound. Okay, so I'm going to say k over n plus z alpha over 2. Remember, we can still use z alpha over 2 because for large n values, right, we're approaching a normal curve, so it allows me to use the z value. So this is k over n, 1 minus k over n, all over n. This is my upper bound. Okay, and this is going to be minus my lower bound, minus z alpha over 2. Okay, my upper bound minus my lower. I'm showing you where all these things come from instead of just giving you formulas to chew on. Right, so this is our upper bound minus our lower bound, just like we did with our continuous data. Okay, and then basically I can say that my width, my margin of error, is equal to the width divided by 2, right? So this is our width. We can bring all these things together, find out, we're going to divide it by 2, and we're going to get this is equal to z alpha over 2, k over n, 1 minus k over n, all over n, inside of a square root. And that gives us our margin of error for proportions. Okay. Let's talk about what happens when we have a fixed n value. Our width is a function of basically k over n, 1 minus k over n. Okay, so basically our k over n, right, that's our proportion, right? The proportion value is between 0 and 1, okay, when we multiply everything out. So in terms of our maximum value, right, my max value is going to be k over n is equal to 1/2, right, because it'll be 1/2 times 1/2. So it'll be 1/2 times 1/2, okay? So plugging in 1/2 times 1/2, that's going to give me a maximum width equal to 2 times z alpha over 2, 1 over 4n, right? 1/2 times 1/2 divided by n gives me 1 over 4n. I can factor out the 4, right? Which is basically going to give me z alpha over 2, 1 over n in the square root. That gives me my maximum width for proportions. Okay. That's going to help us figure out like what's our maximum value. Okay, especially if I don't know what my proportion is. Okay, but I know how many I have, and I can say, you know, for my known proportions, my unknown proportions. Okay, I can just assume my maximum width. If I don't know what the exact proportion is, but I know how many people were sampled, the maximum width is going to be, assuming the proportion was equal to 1/2, right? And that's going to allow me to figure out what my maximum width is going to be. Okay. So let's try some examples so that you can see how this actually all holds together here. Okay, looking at example 4. Okay, everybody have this? I'm gonna put another piece of paper down on top of it.
I'm just copying down the max width.
Great. Let me know when you're all set.
Okay, I'm still writing. Okay, I'm good.
All right, so example 4 in our lecture notes here, lecture examples. All right, so the example 4 says, in estimating the number of auto thefts in some big city, and we want to do it within 2 automobiles, right? So auto thefts, so it's like saying, you know, 5 cars per month. I want to estimate the number of auto thefts within like 2 cars. So it's 5 cars a month plus or minus 2 is kind of how we're thinking about what this means. Some researcher wants to be 99% confident, okay? You want to be 99% confident in the estimate based on the sample that we have. So previous study of looking at auto thefts found that we had a standard deviation of 4.2. We have standard deviation, but we don't have a mean value. Okay, but that's okay. These are academic problems, and we're learning how we're going to be solving this. So how many days should we survey, right, to get a pretty good 99% confident interval of what we're looking at, right? I need to know. I'm so basically solving for n in this case. Okay, given my margin of error and my standard deviation, okay, and my confidence interval here. Okay, so let's write down the different bits that we have. So if we're told it's 99% confident, okay, that means that my z alpha over 2, so my alpha is equal to 1 minus 0.99, which is equal to 0.01. Okay, but remember that 0.01 has to be split between 2 ends of those tails. So we're talking about an alpha over 2 equal to 0.005. Okay, I take this 0.005 and I look it up on my chart right here. Okay, and I'm looking, oops, sorry, there's too many zeros. 0.005. So I'm like roughly right around here somewhere. Okay, 4, 9, and 5. So I'm, whoops, you can't even see what I'm looking at. So I'm like right around here, okay, in terms of my z value. So I find a z value, okay, based on that 0.005. So my z alpha over 2 is going to equal to 2.58. Okay, so I gave you the different z values, but I'm telling you where they're coming from. Okay, they come from our z table. Okay, so I got this from the lookup table. All right, so now we were told our margin of error is equal to 2, and our standard deviation is 4.2. Okay, so we need to solve for n. Okay, so let's put things in. So solving for n is going to be like n equals z alpha over 2, standard deviation all over the error. Remember, n was in a square root, so I have to square everything to get my n out of that square root. So I'm going to, let's see, let's write down where this comes from. So our margin of error is equal to z alpha over 2 sigma over radical n, right? So my error, my e, error is equal to z alpha over 2. So I'm solving for n in this case here, so I get n equals everything here. All right, so now with that case, I'm going to plug things in. So this is 2.58 times 4.2. Okay, sorry, this is not sigma squared there. I've made a mistake. All over 2, my error and that's squared. So multiply things out, right? And I square it, and I find that my n is equal to 29.35. We want whole days, so I'm going to round up. Okay, always when you're dealing with an n that's fractional, round up. Okay, we're going to even if I get 29.2 or 29.1, I'm going to round up to the next highest n. So my n is going to be equal to 30. So I need 30 days to be 95% confident that I can get the number of concepts within a margin of error of 2. Okay, so I've solved for n based on the information that we were given here. Okay. Everybody see what we did? Anybody still writing?
Should we take note of this formula you use?
Absolutely. Yep, right here. These things, like I said, I'll post a formula sheet, but you can, I always tell people, formula sheet's a guide to tell you like the kind of things that show up the most often, but you should start getting into the habit of taking these formulas and then writing them down on a separate piece of paper so that you have them to access very quickly. As we get into the statistics portion of things, we're going to be accumulating a lot of different formulas that we need to use, okay? And so having it on a separate sheet of paper, and you can take the formula sheet that I'm going to post and you can print it and then add your own stuff to it, okay, or make notes on what these things are for, okay? I can't remember if the margin of error is on there, but it may be in a different form. But this is something that you'll want to have definitely written down on a separate piece of paper with a little star on it, because it's something, especially like the confidence intervals, you'll want to have done as well. All right, let's try example 5. Example 5 says, in a given election, they did a telephone poll of 597 registered voters, and it showed that 299 of them supported a particular candidate. And we want to know what's the margin of error with 95% confidence. Okay, so let's take a look at what we have, and this is our proportion right now that we're dealing with. So let's take a look at what we have. So my 95% confidence interval means 1 minus 0.95 is going to give me my alpha, okay, which is 0.05. Okay, now remember, for this I need alpha over 2, 0.025. This is the thing, alpha over 2, that I look up. So my z alpha over 2 is going to be 1.96. Okay, just start kind of prefetching all the information that you're going to need for your margin of error. Okay, so now I need to think about all my different pieces. So let's see, I'm going to go my error is going to equal to 1.96 divided by 2 radical 597. Okay, it's half of my width, right? Which is equal to 0.04. So my margin of error is 4%. Okay, I'm going to do this in a couple different ways so that you can see how it can come out. Okay, I can think about like this. Okay, it's going to look like, in terms of proportions, k over n, 1 minus k over n here for my error. Okay, so, times z alpha over 2. Okay, so now if I assume maximum, okay, I have a specific n value, 299 over 597, but I want to find the maximum margin of error. So I'm going to assume my proportions are 1/2 and 1/2 all over 597 times 1.96. The 1.96 is not in the radical, okay? And that's equal to 0.04, which in terms of percent is 4%. So we have a 4% margin of error, okay? Right, so remember our width, our confidence interval, right? So this whole thing here is our width. Here to here, okay? My margin of error, my error is half of that value. Okay, my error is plus or minus my error, but my confidence interval width is this whole thing. Okay, 4% margin of error in the poll results. That gives us our maximum margin of error, okay, based on a 95% confidence interval. It's also true that A over N is about equal to 1/2. So 299 over 597 is about 1/2 anyway. So we're able to do this maximum value because our proportions themselves are really close to 1/2. You know, if you guys need more time writing that down. You guys, nobody needs more time writing it down? Right. So let's take our ideas of confidence intervals and take a step back and think about sample sizes, right? So how do I choose a sample size, okay, of data? That's a really critical question in research, which is, you know, to be able to have power in your statistics, I need to have a certain number of samples. So let's think about that. So choosing sample sizes. So we're designing experiments. And the experiment is a yes or no question. It's a binomial background data. Oops. Okay, so we take a look, it's a drug trial, or we ask people's perception. Do you hear this, yes or no? Does this drug work, yes or no? That's what we mean by binomial distribution of data. So we need to know how large a sample of data to pull to get within, say, 1 minus alpha, 100% confidence, 95% confidence, 99% confidence, whatever we specify, confidence, being within a d distance of p, our population proportion. So p hat is our estimator. Okay, so we need to know, right, how many samples to get within some distance with a given confidence level of our proportion, our population proportion. So let's write down some ideas. So our size should be no smaller than n z squared all over 4d squared. I'm going to write down a couple formulas. This is where our population proportion is unknown. Okay, if it's unknown, right, I'm going to assume that my maximum width, right, my proportion is equal to 1/2. That gives me, that's where the 4d squared comes from. The 4 comes from that p hat's equal to 1/2. 1 minus p hat is equal to 1/2. This gives us our maximum. Okay. If we know what p is, right, when p is known, we can use the exact values. So n is going to equal z alpha over 2 squared. That's for a confidence interval. P times 1 minus p. That's right. Remember, if p is equal to 1/2, that's where I get the 1/4 from. All over d squared. This n here will be smaller because we know the exact values. Reduce n. This is our max n. This is like maybe an exact n. It'll be smaller than this because this is assuming our maximum value for n. Okay, our maximum value for p. Okay, if we know exactly what p is, then this n will be smaller. Okay, I'll put some stars on these too. These are things you'll want to have on your formula sheet. When you guys are all set, taking a look at example number 6. Choosing a sample size is a really important thing. Being able to choose an appropriate sample size is going to be the difference between whether your study really has power, right? So that when I do some kind of a study and I want to publish it and I want to say, I can make these statements about the overall population, but if I've only polled like 3 people, is that really going to say a whole lot about the overall population? But if I polled 3,000 people, okay, that's going to tell me, you know, I have a much greater confidence in the results of that study, say, for example.
What is D actually equal to?
Yeah, so we'll actually do an example with that, so you can see it's going to be it's the distance. It's basically a representation of the width of our confidence interval. But I'll answer that through our examples here. You'll be able to see it as we go. All right. So now here we go. Example 6. So we want the example 6 says we want to do a public health survey of children who are younger than 14 years old, who are unvaccinated. Find out what that is. The sample proportion of unvaccinated kids is X over N. We don't know what that is. And it should be within 98% probability of being within 0.05 of the true proportion P. So how large should our sample be? What's our N? So this is a solving for N. It's here, okay? So let's think about it. So my 98%, right, is like saying 1 minus alpha equals 0.98, right? So my alpha is going to be 0.02. That's a 0.02. So my alpha over 2 is 0.01. I look for 0.01 on my Z table, and I find a Z alpha over 2 that corresponds to it as 2.33. Okay, that comes from my Z table. Okay, my distance is equal to, they said 0.05. Okay. So now, and my P in this case is unknown. Okay, so we want to be within that range. Okay, so we're kind of using our width, okay, of our confidence interval to say, you know, I want to be within 0.05. That's like our width of our confidence interval. Our N, we have to find out what N values are going to help us get there. Okay, so N is going to be Z alpha over 2 squared all over 4D squared. Okay, I found my Z alpha over 2, 2.33 squared over 4.
I get where the D value did come from. I just, how did you identify it in the?
I was told right here.
Yeah, like how, I guess my question is, how are we like supposed to pick that out?
Yeah,
Like, I'm just a
so
little confused of the meaning of it, I guess.
yeah, so it's kind of like saying, remember when we calculated our confidence intervals before, we had like our sample means, right, plus or minus Z alpha over 2 sigma over radical N, right? And it was going to be based on our sample values, or in this case, a proportion value, right? And so what we're trying to do is we're trying to say, you know, this value, right? We don't know what N is. N is what we're solving for. But I know that my I've got my proportion, I've got my confidence width, okay, is going to be 0.05. So I want to be able to find out based on the width of my confidence interval, right? And the width of my margin, basically my margin of error is half of my confidence interval. So I want that to be my distance, right? Let's see, where were we here? With our margin of error, right? So our margin of error, we're looking at these values here. Okay, so my width divided by 2 is my sigma over radical N. Basically, I'm looking at my width, my proportions. I lost my paper. Yeah, and my width of my proportions here. So I'm looking at using these values, right, to help me, right? My maximum width is going to be Z alpha over 2, sorry, 1 over N square rooted, right? And so essentially we're using our confidence interval, okay, to help us figure out like how close we can get within this value. We say we want to get within a margin of error, within a distance of 0.05. Okay, so that's like within a distance of let's see, how can I say it? Our population proportion is going to be within 0.05, okay, on either side, but I need to know what size N is going to help me narrow that down. So I'm kind of back ending it. Instead of saying I surveyed all these people, what's our width gonna be? You know, the width of our confidence interval with 98% confidence, what's that width gonna be if I've surveyed all these people? Now I'm saying I want to be 98% confidence. I want to be within this small range. 0.05 is a pretty small range, right? I want to be within that small range around it. So I need to know how large of a sample size do I need to go in order to get that. So instead of, we're kind of looking at our formulas and our experiments in a different way, okay? Instead of telling you how many people we've surveyed, right? And then saying, what is our confidence interval? What's that width of the confidence interval on either side, right? We're saying, I want to fix that width to be this. I want to find out what n I need in order to get that. So all we did was rewrite our equations, right? Our confidence interval and our margin of error came from the same thing, okay? Because our confidence interval and our margin of error is half of the width of our confidence interval. So we're basically looking at using, okay, our distance, right? Our margin of error distance, and our z alpha over 2. And this is like our maximum. So we don't know what the proportion is. So I'm going to assume like this 1/4 assumes the proportion is equal to 1/2, because it gives me p times 1 minus p gives me 1/4, right? If they're both equal to 1/2. So that's where this is coming from, because I'm specifying parameters. That'll often happen when you're doing experiments, or when you're like working for a company, or say if you're working for a law firm and they're trying to gather data. You know, is this group significantly different than that group? Or we want to get, you know, these values within within a certain parameter set. And so we need to make sure that the n that was chosen, or that the n that we choose in order to get values within that, is going to be appropriate. I don't know if that helps. I'm kind of rambling a little bit, but basically we're trying to
No,
yeah, it's kind of confusing, but we're essentially trying to say, we're trying to fix all the parameters and then find out how many basically participants within our experiment we're going to need in order to get the statistical power. And that's a common thing when you run experiments is, you know, how many, you know, subjects do I need to have in this experiment in order to have 95% confidence, or to get my values within a certain width, for example. It's a question that you'll have to answer when you do experiments, either on co-op or out after you graduate too. Okay, or somebody will tell you, and then you can say, hey, your n isn't high enough to give us this kind of a confidence interval, or our confidence interval is going to be not as confident because our n is small, say, for example. Right. So I plug everything in, and I get 542.89. Okay, but these are people. I need to round this up. So n is going to be 543. Okay, so that's how many people I need to have in order to satisfy all these parameters. 98% confident, okay? And I want my values, my proportions, to be within 0.05 of my population, okay? Because I don't know what this proportion is, x over n, so I'm going to assume my maximum interval, okay? Given the maximum interval is p, the proportion is equal to 1/2. Okay. You guys have that okay? All right. So one of the things that can happen is if we have your book has some examples like this, so I'm going to go through, I think there's maybe like 1 or 2 homework problems like this. So if we have a small finite population and we want to be able to estimate a proportion, okay. So I've got a small finite population. I want to be able to estimate the proportions on that. So we can say that an approximate confidence interval or proportion of a small population. You have to do a little bit of a correction. So let's say that n is our population. Okay, a population of a small town, say, for example. We have a sample size equal to small n, okay? And then p hat is our maximum likelihood estimator of our population proportion. Okay, so given big N, small n, and p hat, right? So if I want to come up with a confidence interval, I'm going to say I've got p hat plus or minus z alpha over 2. We start off the same, and then I need to do a correction. So p hat 1 minus p hat all over n times big N minus little n all over big N minus 1. It's a correction factor, okay? Oops, can't see the proportions. Okay, so this is our correction factor part. I think you maybe have a couple homework problems that are along that line. We'll do an example. Example 7 is our last example for this chapter.
What is the MLE stand?
Maximum likelihood. I'll write that down here. Okay. All right, so this gives us our correction for our small population sizes. So we'll do an example. Example 7 is going to use this here for that. You guys all have this here?
I'm just copying it down.
Give you a second.
Okay, I'm good. Thank
Okay, great. All right. So example 7 says, we've got a researcher, they're studying a population of a small town. So our big N is equal to 2,000 people. So we're just looking at this town, has 2,000 people in it. And they want to make an estimate for a proportion for, yes, no surveys on a question. This means, this is telling us it's binomial, it's a proportion. The background data is a binomial experiment. So how many people, small n, does the researcher have to randomly sample? And we're not going to do replacement. We're going to assume each person is independent to ensure that our p hat, our estimate, are within 0.04 of the true population. So E is our margin of error within the true population. Okay, so they don't tell us, but we're going to assume we're going to do 95% confidence. If you're not told what confidence level to assume, do 95%. It's the most common, and it's the most, statistically, it's probably your best bet statistically for all the reasons we talked about earlier. Okay, which is going to make our alpha 0.05, our alpha over 2, 0.025, which makes our z value 1.96. Okay, that corresponds to alpha of 0.025. Okay, so now, right, our p hat is going to equal to, p hat plus or minus our margin of error is equal to p hat plus or minus, we were told 0.04. Okay, so now I'm going to take this and I'm going to plug things in and I'm going to solve for n. That's my goal. Okay, so let's do that. So I've got my E is equal to z alpha over 2 p hat 1 minus p hat over n times big N minus little n, big N minus 1. Okay. So this is our margin of error, right? I'm going to plug things in, and I'm going to solve. My goal is to solve for this little n right here. Okay, so I reworked it. Okay, did all the algebra. I'm going to give you, right, if we solve for n is equal to z alpha over 2 squared p hat 1 minus p hat all over our margin of error squared divided by, right, where we're dealing with this here, we have to solve n minus 1 over n plus z alpha over 2 squared p hat 1 minus p hat all over big N, oops, you can't see what I'm doing, big N e squared. Okay, so this equation here, right, reworked in order to solve for little n becomes this equation right here. Okay, so I'm just going to plug things in because I have all of my information here. Okay, and I'm going to work it out. So I'm going to get 1.96 squared 1/2, 1 minus 1/2. We don't know what p hat is. Okay, so but we're going to assume it's equal to 1/2 to find our maximum. Okay, all over 0.04 squared. Okay, and I'm going to start playing. So 2,000 minus 1 all over 2,000 plus, it's really busy, 1.96 squared times 1/4. This is p hat times 1 minus p hat is 1/4. That's a 4. 1/4 all over 2,000 times 0.04 squared. Okay, multiplying everything out, adding, dividing everything out. Watch your order of operations when you're doing this, right? We're going to get 461.86. I need to round up, which is going to give me 462. I go for n. Okay, that basically says, right, I'm going to make the assumption this is my maximum n value because I don't know what the population proportion is going to be. We want to come up with an estimate for that anyway. So I'm going to assume my maximum number of n values that I need to do in order to get my data within 0.04. Okay, because I want my values to be within 0.04 to solve for my population proportion. Okay, this is always a trade-off, right? Ultimately, we would like to be able to pull all 2,000 people in this town, right? That would give us a really great estimate. That would just give us the whole population, okay? We would be able to say, you know, in that case, 100% confident that we've got everybody in the town. Often what happens is it costs a lot of money to pull all those people and then to run the statistics on it. 2,000 is a small number, but you can imagine if we had, like I said, 7.5 billion, it's not feasible to do that. There's always a trade-off between being able to get a larger n value and getting my confidence level really high, right? So if I want my confidence level really high, I want to have a really large n value, but that's going to cost a lot of money. So maybe I can lower my confidence level, you know, to 95%, say, for example, which is going to help me lower my n value. So it'll save me money, but I'm still 95% confident of the data that I'm gathering, okay? So that's why we're always looking for what's the value of n, how many samples do I need to get in order to get within a certain confidence level or a certain margin of error, okay? Because it costs money to run surveys and it costs money in order to, you know, gather more and more data, right? So that's why we're looking for that sweet spot, you know, which is in this case 462 out of 2,000 people to help me get 95% confident and to get my p hat estimates are within 0.04 of my population proportion. Sound good? It's a lot to take in. There's a lot of nuances and a lot of information about what's going on. And I think I'm not going to start chapter 5.4 right now. We'll start tomorrow's class with chapter 5.4. It's very quick. And then we'll do 5.4 and then we'll start in on chapter 6. Okay. 5.4 is a little bit of a segue back to estimators. Okay. And then chapter 6 starts using our confidence intervals and being able to do hypothesis testing and thinking about statistics more. Okay. Again, as a reminder, in office hours today, I'm going to go over the midterm exam. And like I said, I'll film it, I'll video it. So then I'll post the video for that as well if you can't make it to office hours today. But I encourage you to take a look at it so that you can, you know, understand how to do this material because it will be on the final exam. Okay. All right, guys. Have a great day.
Thank
Take
you.
care.